And I'll pass you on to one of the gurus in calibration and validation, Dr. Kurt Tony from Asagoda.
Thank you, Cindy. All right, so let me start. First of all, if I'm out here, can people hear me okay? Especially someone in the back. If you could. Okay, I will I'll try to stay at the microphone, but I am a very just hyperactive. Hyperspectral obviously translates. So hyperspectral is too many bands, hyperactive is too much activity. My hands will be all over, I will be wandering, I will try not to frustrate you. I will also try not to speak too quickly. If I start talking too fast, you just become hyperactive and tell me to slow down. Normally we try to make sure people have notes and everything, but since we were not able to get you the material ahead of time, please tell us to slow down if you need to. Overview of the course itself. So basically the idea of this is to try and go through the basics of a vicarious calibration and to show you how to do error budgets using that vicarious calibration as an example. And it's going to be tailored toward imaging spectroscopy, realizing that much of my background is multispectral as well as hyperspectral. It does not depend upon the number of bands. The work we've done in the past really does not pay attention to the type of sensor other than are we calibrated or not calibrated. But the goal here is because of the sponsorship is we are trying to ensure that we show you how you would take what we have in this course and apply it to a specific case of imaging spectroscopy. There are 3 days, so hopefully everybody knew that that's what they signed up for. So today, tomorrow, the day after. And it's going to be broken up into several pieces. And as I go through this introduction, you'll see they're broken down into roughly 20-minute little tiny lectures, so that you get an idea of how much time we're trying to spend on each of the topics. I want to make sure I acknowledge what Cindy Ong was talking about, the IEEE GRSS and GSIS Technical Committee for sponsoring this training course. There will be 4 instructors for the material. Myself, Chris McClellan, who's in the front row over there, Cindy, who also you saw, and then Martin Bachman, who is unable to attend, pretty sure most of today. He will be here tomorrow to talk about the atmospheric. And the photograph here was taken basically at a meeting that was in Edinburgh that Chris sponsored, or he hosted us to talk about calibration and validation of imaging spectrometers, and that's when the idea for this training course got some movement towards completion. It had been discussed at previous technical committee meetings, and so the idea was to try and bring this together and take advantage of the IGARS meeting here in Beijing to do this. Each of the persons there's a bit of a biographical introduction there. Myself, I'm at NASA Goddard Space Flight Center right now. If any of you happen to go back into the old literature, many years ago, you'll see me affiliated with the University of Arizona, and that's where I first did most of my work. I also did my graduate work there as well. But in atmospheric sciences was my PhD, and then moved into optical sciences for many years as a professor there. So what do we hope to accomplish today in the morning, so before lunch? And so we have roughly 2.5 to 3 hours. This material really is at the 3.5 hour estimation right now, but I think I can speed things up on the reflecting space to catch up a little bit of time. I will not speed up just for the purpose of trying to meet a schedule. There are places where I can skip charts because it may not be as important, and we will give you the charts. I'm not certain how we are going to do that.
At the end of the course, I'll give you a USB stick with all the material that we've used.
So I'm not certain how many of you have done something like this before, but oftentimes it's just easier to put every chart you might think you want into a package, and then as you're talking, you pick out the ones that are really important. Some of that happened with my preparations, so I apologize that I was not as diligent in preparing ahead of time. But the nice thing is you will get more information, but I will try to hit the high points, and then there will be added information that you can go back to get details if you need. So in the introduction to the calibration, I will start with the general terminology, and I will hand it off to Chris McClellan to talk about the calibration concepts and the pre-launch characterization, and then I will come back and talk about the in-flight characterization and calibration. And then we'll have a little bit of a break, stretch our legs, wake up a bit, and then we'll go into reflectance-based method overview. And in this process, it's starting off with what the basic approach is, some results that we've gotten in the past by using this method, discuss how we pick our sites, TOA radiance, top of atmosphere radiance, uncertainty sources, and error budgets. Because ultimately what we want is this error budget discussion. And we're going to use this reflectance-based method because that's what I have used for many, many years. We're going to use this reflectance-based method as the teaching tool to get to how do we do an error budget. Because that's something that we see within the community that is not well established right now. It's something that we want to train people how to do a good job on error budgets. And then this afternoon, after lunch, we'll cover the conversion of digital numbers, DNs, to a spectral radiance, because that's something we need to do the calibration. Because in the reflectance base, we compare a predicted radiance to what the sensor is measuring, and then that's how we get our calibration information. And then start into the details of the methodology. And the first one we'll talk about is the atmosphere. Again, basic concepts, equipment, measurement approaches, example results, uncertainty sources, and then an error budget discussion. Tomorrow morning, details about the surface measurements for the reflectance-based approach. Again, the concepts, the approaches, the equipment, very similar to what I just described for the atmospheric case. Then the rate of transfer, Martin Bachman will cover quite a bit of this in terms of the basics of rate of transfer, the inputs, some example results, and then I will talk about the uncertainties in terms of how we go from our measurements to a number of photons out the top of the atmosphere. And then tomorrow afternoon, sensitivity analyses. So we talk about error budgets, and a lot of what we do in terms of error budgets are really we start by doing sensitivity analyses to find out where our largest sources of changes might be because we modify an input. So I want to discuss that, and then get into a discussion of the error budget itself from a true metrological standpoint. So it's trying to train people into traceability, uncertainties, and things like that. And then on the third day, Sunday morning, start with site selection and site selection for imaging spectroscopy. And much of this work Cindy's been doing, and she and I will trade off in terms of covering this material, talking about the examples of what we have right now, and then she'll talk about some of the work she did in trying to find a suitable site for future imaging spectroscopy work. The one thing that's interesting is the site selection practical session. This will be an experiment. Hopefully we'll see how well it works out. We think it will be fine. But rather than have you spend 3 days sitting there and listening only to us, we want to see if you actually gained anything from the discussion and have an experiment to let you try to apply the methodology and come up with an answer to a question. The question will be basically, you have to choose a test site for doing a calibration. And there will be, I'll tell you right now, we'll re-emphasize it, there are no right or wrong answers. What we're going to teach you through this whole material is that you justify the answer you give. I picked this site because this is important, letter B is important, letter F is important, and that means that I'm going to pick that test site for what I'm going to do. That's the type of lesson we want you to get from this material. So we'll talk about the results of that and also some of the things that are happening in terms of the next 5 years for imaging spectroscopy. And then the conclusions and a wrap-up in the afternoon on Sunday. And it's where do we go from here? How do we get better at what we're trying to do? And I'll spend a little bit of time talking about Clario and Truths. Clario is a project I'm working on with NASA to do climate remote sensing. And if we were going to hand it out, what I was going to do is in the United States, if you do a seminar, they have what's called seminar bingo. And has anybody played bingo? Does anybody know what that game is? So in bingo, what you have to do is try and fill in each of the boxes. And if you fill in a box along a row, or along a column, or along the diagonal, then you win. You say bingo, and you win. And in this case, it's if one of us falls asleep, we get to fill in that box. If I run out of time, which you notice this is the free box, because every speaker runs out of time, I will try to bring things up periodically with what I think is humor. If you think it's supposed to be humor, it's in your interest to smile, at least. Because otherwise I will start to explain it, and I spend way too much time trying to explain my very bad humor to get people to smile. And it's more just relax. I tend to do much better if there's an interaction. So please do not hesitate to ask questions. Please do not hesitate to point out where you might have something of interest that is related to what we're talking about, that expands the material, that can help the rest of the class, especially if it's something that's specifically related to your efforts. So I will ask, and I suspect I will not get a response, but I will ask if there are any questions or comments about the outline. I went through it in about 10 minutes. Do many of you do telecons? Have you had the joy of being on telecons? The joy of a telecon is when somebody goes, anybody on the phone have a question? And there's no answer. Nobody says anything, and it's kind of difficult and so forth. But at least I can see you. I do not think anybody's on the phone doing this. And periodically I'll put a cartoon. In this case, you only have to know this last piece here. 90% of our job is figuring out how to label things, what we're going to call it. So this very first part is just the terminology. That's because for each of you in this room, there's a set of terms that you're using specifically to what you're doing. I am going to try and at least make it so that what I'm using in this material and all the things we're going to be talking about in the next few days, you have a slight translation of what you might know it to mean and what I am discussing. And in some cases, there are some terms that are very important, and we want to make sure that you know why you should be using this particular class. So I'm going to talk about spectral and radiometric terms and energy terms. Radiance, spectral radiance is a key element to what we want to do in this class. So spectral terminology, ultraviolet, visible near infrared, and after this view graph, I will almost certainly just start saying SWIR and VNIR. So this is one of the reasons I put this up here. Shortwave infrared, SWIR, 1.1 to 2.5 microns, or 1100, 1100 to 2500 nanometers. VNIR, visible near infrared, covers roughly 350 nanometers to 1.1 microns, 1100 nanometers. Have any of you ever wondered why we have the VNIR? Why that's a specific label, visible near infrared, VNIR. So if you work with history, you work with Hyperion, they talk about the VNIR telescope, they talk about the SWIR telescope. And that's because the VNIR is where silicon operates. So we use silicon detectors whenever we can because they're very inexpensive, they're very good, but they cover roughly that 350 to 1100 nanometer spectral range. So then we needed something to cover beyond that because we want to talk about the reflected solar. So the part of the spectrum where sun energy is the dominant source of our light, that covers everything from 350 to 2500 nanometers, 0.35 to 2.5 micrometers. So if we have something that covers up to 1.1, we need a label for something for 1.1 to 2.5, and we came up with SWIR. You have to be very careful because if you talk to, in the United States, if I talk to a builder of satellites, they just call it infrared. And that's very dangerous because infrared can mean anything from basically 1.1 micrometers all the way out until 50 micrometers. And so you just have, so these are the definitions I will stick to. I will try not to go VN or SWIR, but I cannot promise anything. It's a natural usage of the terms. Geometry. Zenith angle, view angle, elevation angle. Elevation angle is the easier one to start with. I'm looking straight ahead, I go up, I'm elevating, that's my elevation angle. If I'm looking straight up and I come down, that's the nadir angle, or the zenith angle. So I'll use zenith angle and radiative transfer all the time. We're going to talk about the solar zenith angle. That's measured from straight up. It's very important because when we start talking about radiometry, if you mix up elevation angle and zenith angle, you can get some very different answers. Almost all examples I try to use, I use 45 degrees, because then it will not matter which way you go. But if you have a 60-degree zenith, that's much different than a 30-degree zenith. And then the view angle, your satellite looking straight down. The view angle is 0. And then if we go off nadir, we're looking away from 0 degrees, we go to larger view angles off to the side. Resolution: temporal, spectral, spatial, and radiometric. All right? How often you collect, both in terms of daily, in terms of what's the shutter time, what's the integration time. Radiometric resolution, what's the largest range of total photons I can cover, dynamic range. What's the smallest little interval I can measure, things like that. Spectral resolution, in terms of imaging spectrometry and imaging spectroscopy, we'll spend some time on this, but it's basically the band spacing, the smallest band that you might have, and the overall spectral coverage. And then spatial resolution, I really feel for anybody who's not a native English speaker with spatial resolution. High spatial resolution. Why that means the smaller thing, I've never figured that out. Because if we have high spatial resolution, we're seeing 1 meter. If we have low spatial resolution, we're seeing 1,000 meters. And it's backwards, but that's just the way we label it for whatever reason. And I'll use it, as I go into some of these, I'll go into some of the details. GIFOV and GSI. I'll just stick with this pixel size or spatial resolution, but if you have learned ground instantaneous field of view or ground sample interval, that's basically what I'm referring to. And every example I'm going to assume that the ground sample interval, how many times I'm actually grabbing something off the ground, that ground sample interval equals my pixel size, equals my GIFOV. So if I have 30 meter spatial resolution, I'm sampling every 30 meters. I'm just going to keep it simple that way. Where spatial resolution plays a role is, what are the features we can see, and this lower right should disappoint you. That's a basketball stadium in the United States. And now all of you have grown up watching Google and all these high resolution, and GFI is the high resolution system. That there would be much better spatial resolution there. But it gives you an idea again, is we have radiometric values in each of those spatial locations. Swath width is going to play a role in terms of how we do our vicarious calibration. If I have something that has a 55-degree swath width, I can do collections almost every day at a test site. If I have something that has only a 5-degree swath width, I might only get a data point every 30 days, maybe even larger. So that's why spatial resolution and swath width plays a role in this discussion. Spectral resolution. If I told you you had the choice of the left or the right, how many people want the right-hand case? See, I've done this class a lot, or these kind of classes. You notice I always pick the one that's the negative first. I'm not going to ask you how many would pick the left, because I'm going to go, perfect. Not many of you wanted to go with the right-hand case, because we're doing imaging spectrometry. This is closer to imaging spectroscopy and imaging spectrometry, so that's the case we would have wanted. Right? It's all about, I've learned, you either don't answer because you don't care, you do not answer because you're not listening, you do not answer because I'm not a very good teacher, but at the very least is we make sure that somewhere I'm acting like I'm talking to you as opposed to just lecturing. So hyperspectral, lots of bands. Multispectral, not so many. And how we define the spectral resolution, the right-hand case, I could still have, for these bands, I could have higher spectral resolution than in this case. Because each of these bands could be narrower in what they measure, as opposed to here in terms of number. And that gets us into a discussion of these different kinds of situations. The multispectral case, not going to spend a lot of time on this one, because we don't care as much, but it's in the chart package. Airborne systems, because when we start talking about hyperspectral imaging spectroscopy, most of you will probably have seen or will see an AVIRIS image from JPL, airborne system APEX from Europe. There's a lot of airborne systems that are out there. Hyperspectral, so you have the HyperCube. The idea is that we have now, we can do spatial, as well as we can do many spectral bands, and we can do a lot of things with those extra bands. Some of the examples here, AVIRIS, Hyperion, EO1, but it potentially allows for discrimination of surface features. So spectral signatures. And the reason, and I have several just examples of spectral signatures, and I'll put them in the package and let you see them, but the reason that this is important is because it's the height of these features relative to the bands around them that allows us to then discriminate what might be at the surface or what's in the atmosphere. If we do not know where those are, spectral calibration, if we do not know their depth, radiometric calibration, we cannot do as good a job as we would like to. So it's important for us to have an idea of that. And then I have in here just some examples of where it stands relative to the human eye. We only cover a very small part of the spectrum. Some of the features that you might see in terms of the red edge, in terms of wheat, sugar beets, and things like that. These are all standard things. Has anybody been to what I call night talk? Alunite, Montmorillonite, Illite, it's kaolinite. There's not many geologists in the room.
That's the fun part of it. That's why we're doing it.
That's right. Well, some of us are land vegetation types. I'm an atmospheric scientist by trade, so I would rather be looking at the water vapor and things like that. If you can avoid an Ike talk, if you're not a geologist, you can play Ike bingo if you want. Okay, all of the minerals end in Ike. That's the joke. Spectral selection. Peak transmittance, peak wavelength, bandwidth, center wavelength. If I wanted a better bandwidth, and it's not a trick question. If I wanted a better bandwidth, would I want to go narrow or wide? I'm trying to do spectral discrimination. Would I try to make my bandwidth narrower or wider? How many want to go narrow? Okay, good. That's the right answer. It does not mean, it's not as easy as that, because if I go narrower, I get less energy, and so now I need a better detector package, and so there's a trade between how wide and narrow we make these things, but that's the definitions. As we're talking, when I say bandwidth, and when I talk about spectral resolution, I will talk about bandwidth, which is different than a lot of imaging spectroscopists. It's a bad habit I have because I came in on the multispectral side first. So bandwidth is my spectral resolution. And I'll repeat that a couple of times. So in this case, the Hyperion system has both better band sampling as well as better bandwidth. It has a better discrimination in terms of number of bands, and it has a better discrimination in terms of bandwidth than Landsat does. Landsat has a slightly better radiometric quality, though, because it's getting more photons. It's collecting over a broader range. So there's all these trades, and it plays a role in terms of the calibration, because how we have to characterize our materials and the things we're doing and the rate of transfer will depend upon what we're trying to compare to. So my measurements will be, in one way, different for Hyperion than they will be for Landsat. Radiometric resolution. These two images are the same spectral band, roughly the same spectral resolution, the same bandwidth from MODIS. But one has been decided, or one has been developed to look at oceans, and the other one's developed to look at land material. And they did this by changing the radiometric resolution. They changed the dynamic range and how the system converts photons into the digital counts. So in your head, try and decide which one you think is the one that should be used for oceans.
right one?
Yep. This one's for oceans. All the clouds get saturated. All the clouds go to basically unmeasurable, so that you can get more detail in the dark stuff, which is the water. So on the right-hand side, you can see the clouds, you can see the land, and this plays a role again in terms of I cannot calibrate this band on many of the test sites I'm using. I can calibrate this one. So then I would have to find a methodology that allows me to go between the two of them in order to calibrate the one here, or I have to pick a different site for my vicarious calibration. So I'm going to try and go through some radiometric terms reasonably fast. The one I want here is this radiant flux density, and this radiant excellence is really the big one. And it's irradiance. Irradiance is a watts per meter squared. And it's important because we're going to be talking about solar irradiance. The others are there that you can use them to get an idea of what I'm talking about later on. In terms of radiometric terms, also radiance is a really important one. I will do everything I can to operate in radiance because radiance doesn't care about how big my sensor is looking, what the field of view is, what the swath width is. Doesn't care about, as long as I have a homogeneous surface, I can go any altitude above that surface, I can use any field of view for that surface, I will get the same radiance. Radiance removes all of the sensor-related problems. Bandwidth, if I go to spectral, and then basically the optics. So just to drive it home, it's between these two cases.
Hey, Kurt,
Oh yeah.
can I ask a question? What is the unit of radiance?
I should not have glossed over that quickly. Watts per meter squared, there's a typographical there. It should be watts per meter squared per steradian. Steradian is a solid angle term, but that's what makes it different. And the steradian gets rid of the optical element effects. If we go to spectral, it's watts per meter squared per micrometer. Imaging spectroscopy people, I've never gotten used to it. They'll do watts per centimeter squared per nanometer. And there's about a factor of 10 difference between those two. So, thank you for bringing it up. These units are really important. You can call anything you want. Whatever we could call this, I don't know. We could call them, is that radii on the very left-hand label of that top picture over there. So my eyesight's not so good, so that's the only word I can make out over there. We can call them radii. As long as I put watts per meter squared per steradian, everyone else will know what I'm talking about. And so in this case, if I can, I'm looking at a surface that's homogeneous. These two sensors will both report the same watts per meter squared per steradian, the same radiance. I can even widen the field of view of the other sensor, and I will still get the same radiance. Now, there should be something that bothers you about this. You're going, well, there's no way that would ever happen. And you're right, there's no way this would ever happen. Because at the very least, I'm not going to find a homogeneous surface. So this should be the first example of I'm going to say things that you do not like. And it's because I'm making assumptions that are not realistic. Anybody ever have a physics class? Anybody ever heard of a frictionless string? Or a frictionless surface? Or a frictionless anything? It's something in physics because it allows them to talk about how momentum transfers. There is no frictionless surface. There is no homogeneous surface. Emissivity, absorptance, and reflectance. Reflectance is the one that's important for what we're doing here. Reflectance, at a very simplistic view, is the amount in, or the amount out over the amount in. The amount reflected over the amount incident. Tomorrow we'll talk about a few more complications to this. Maybe 20 or 30 complications. Everything that we've talked about can be spectral. So remember, I had the Hyperion case, many, many bands, narrow bandwidth, and I had the Landsat case, very wide band. If I go to spectral radiance, I can make them directly comparable. I can remove that bandwidth effect. I may still have a physical thing underneath there that causes me problems. That may still be an issue. But in terms of what we're doing here, we can at least remove the influence of the bandwidth from a sensor-related standpoint. So it allows me to do comparisons between two different sensors that are collecting more energy and less energy. So spectral radiance, we've talked a bit about this, but it gets rid of all the temporal center wavelength effects. There are a lot of assumptions in this particular situation. Cosine law. Winter. And it doesn't matter if it's northern or southern hemisphere. Winter, I won't pick the month, but winter, whatever hemisphere you live, tends to be cold for most people. And the reason is, the sun is lower. The sun doesn't rise as high. And that's because cosine law. So the amount of irradiance we get onto the surface is related to the cosine of the angle of that energy as it comes in. So the energy from the sun is coming in as a kind of what we call plane parallel beam. And if it comes in at an angle of 60 degrees zenith, I only get 1/2 the energy than if it comes in at 0 degrees zenith. Left-hand image is January. Right-hand image is June. I'm using display that's the same stretch. So they're equivalent in that regard. The only reason the right-hand image is brighter is because there's more photons. The sun angle, this is northern hemisphere, so the sun angle is much higher and the sun is much higher in the sky. Elevation is much larger, zenith angle is much smaller. And again, this plays a big role because now I can cover a factor of 2 in spectral radiance at a single test site, as long as I go in summer and winter. 1 over r squared law. As we move away from things, this is going to become important when Chris gets up and starts talking about laboratory calibrations, and we have lamps, and we're talking about distance from the lamp, or if we're talking about the solar irradiance changes as a function of the here because we have an elliptical orbit. We don't have a circular orbit. We're closer in January than we are in July. And so if we double our distance, the amount of irradiance from that object goes down by a factor of 4. And so again, this is just to expose you to the term. Later on, you'll hear me talk about, well, we have to take into account distance squared, or there's a distance square law. This is what I'm referring to. And in terms of lamps, it can play a big role, and I can start to look at the irradiance from a lamp at 50 centimeters is going to go down by a factor of 4. So if I need to reduce the energy, I can do that by changing the distance.